during the weekend. So we should get started with our next lecturer, who is Romeel Davé. Romeel did his PhD in the US in at UC Santa Barbara, I think.
Santa Cruz.
Santa Cruz, sorry.
Oh, that's very loud.
Common mistake.
Santa Cruz, yes.
And he is one of the leading people in the world doing the largest, well, I shouldn't say largest, but the most precise cosmological simulations to date. And he's also chair of physics in the University of Edinburgh. Did I spell that correctly? In Scotland. And it will be a pleasure to have him here talking to us about the cosmological framework.
Great. All right. Well, thank you, Raul. And yeah, thanks to Jose and all the organizers for inviting me out to this. It's really exciting to visit here and see all the people. Yeah, so as he said, I'm from University of Edinburgh. That's how to pronounce that. So if you learn nothing else from my lectures, it's Edinburgh. That's the Royal Observatory. It's a historic building where I work. It's pretty nice. Yeah, so I'll be giving a series of lectures on the galaxy formation in the cosmic ecosystem. And hopefully by the end of it, you'll understand kind of what that means. The general outline is, in this first lecture, we're going to start from the large scales and move in. Okay, so we're going to kind of flip scale completely from what you've been doing in the first week. Okay, and start of the very largest scales and the earliest times, and work our way towards understanding how galaxies form. I am as Raul said, I'm mostly a theorist, a simulator. So this is going to be more of a theory-heavy series of lectures. But essentially what I want you to take away from this, and the way I've sort of geared these lectures, is what should every student know, regardless of field, what should every student know about how galaxies form, right? From the Big Bang. So that's where we're going to start. Okay. So let's start. You all know what this is, right? This is the cosmic microwave background, right? Picture from image of the entire sky from Planck. And what it is, of course, is a picture of our universe at a time when it was 380,000 years old, redshift around 1100. And what you're seeing here in these red and blue spots is effectively the gravitational redshifting of photons coming from the potential fluctuations that are at that time, okay? So obviously that potential well, then these small fluctuations of potential well trace the mass distribution. So effectively this is a mass map, right? And you have a matter fluctuations that are mapped out by Planck at very precise levels. So this is what we know we can start with, right? These are our initial conditions, if you want to think about it, right? These are the initial conditions of our problem of how to form galaxies. The thing to note, of course, is, as you're probably aware, the fluctuations are extremely small, right? It's like a few parts in 10 to the 6 here in mass, and so that is highly in the linear regime. But when we go out and take a picture today, the universe looks very different, right? And this is what it looks like. This is just a JWST image from the JADES team. And what you can see is a whole bunch of dots, and of course every one of these little dots that you see, or little extended objects, pretty much is a galaxy, right? So many millions, billions, trillions of stars, except for a few things, where you see the diffraction spikes, those are Milky Way stars, but other than that, it's basically all galaxies. So that's the problem we're trying to solve. How do we get from A to this, right? And so that's the problem of galaxy formation, and it's one of the most active and dynamic fields in astronomy today, and the main reason why is because it includes a huge range of physics. It's kind of, in a sense, the bridge between small-scale processes and processes that, of sort of early universe cosmology, the large-scale structure, right? So obviously cosmology is going to play a role in galaxy formation, but galaxies, at least most of the light that you're seeing here, comes from stars. So therefore, stars are very important. How stars form, how stars evolve, how stars blow up and spew their their heavy elements that they created in the supernovae. Dark matter, of course, plays a large role in this, and so it's another factor that the nature of dark matter could play a role in how galaxies evolve. Black holes, we'll talk about that a lot in the third lecture, and the role, there seems to be a black hole, a supermassive black hole in just about every sizable galaxy, and it seems to have very strong impacts on the galaxy themselves. So how does that come about? And in general, we'll talk a lot, starting next time mostly, about these feedback processes. And feedback processes in general are just energetic release by processes of galaxy evolution that slow down, that are sort of self-regulate galaxies. So to understand galaxy formation, we're going to have to understand all of these elements. And that's difficult because each of these things is itself sort of a field in astrophysics which is not all that well understood. So, to be a galaxy formation theorist, you have to be a little bit of a dilettante, so that means, someone who knows a little bit but not very much about everything. And so that's kind of how it is, and you have to understand how it all fits together. Okay, so the framework for this is generally this concordance cosmology, lambda CDM, which, as you know, is supported by a wide variety of observations. We'll talk a little bit about some of the observations that are most relevant to how galaxies form, but I just to get everybody on the same page, I'll just outline what this model says. Okay, so it's a Big Bang cosmology. So that means it's saying the assumption is that the universe starts in a very hot, dense state, about 10 to the minus 43 seconds past the time of singularity. Okay, now people often go, well, was the universe ever a singularity? Well, probably not. What this limit is basically the limit of our knowledge, not the limit of the universe, right? It's essentially, we'll talk about that in a minute, but nonetheless, it's a very hot, compact state where the entire universe is squeezed down. And then, of course, it expands, and we have this temperature, which is today's temperature divided by the expansion factor. The expansion factor, this little a, is essentially something that is set to 1 today, but of course was smaller in the past, right? So the temperature was larger. And it's linear with that just because of adiabatic expansion, at least during the matter epoch, right? So then there's, very early on, there's a very important period for galaxy formation, which is called the inflationary epoch. You see the times are very small here. And this is the time at which it was believed that the strong force split off from the electroweak force. And at that time, before that, there was a symmetry. There was a symmetry between the strong force and the electroweak force. And in a practical sense, what does a symmetry mean? It means that the force carrier of the strong force was indistinguishable from the force carrier of the weak force, like the Z or W bosons, or the photon. And the reason for that, of course, is that everything is at such high energies that the masses of these particles are all effectively zero, like a photon, right? And so they all behave kind of the same. But then, as the universe cools, the symmetry breaks. Now, as you know, from like cracking ice or something like that, whenever symmetry breaks, you release energy, okay? And that energy drives this inflationary epoch. We believe the universe is geometrically flat. We'll talk about why in a minute. So that means it's just, satisfies Euclidean geometry on large scales. And there's a mass energy budget, which again we'll talk about a little bit, which is the matter components, the radiation components, neutrinos, and dark energy. And the main distinction between these components to a cosmologist is how the densities evolve with time, okay? And that's really what distinguishes one type from another. And then the whole thing is described by general relativity. Essentially, you have an isotropic homogeneous fluid in a expanding metric, and this is worked out by a number of authors, Friedman, Lemaitre, Robertson, Walker, in various forms, and provides a very good description of the universe on scales. Okay, so just to sort of, again, show this in more pictorial form, right? So this is the early universe timeline. Here's the Planck era, so this is the Planck time. Above that energy, essentially the universe, we need to know how gravity is unified with the other three forces, and we don't know that yet, right? Maybe ever, I don't know. Then you have this quark-gluon plasma. This is the epoch of inflation. This is a logarithmic time scale, so it really emphasizes the early universe here. We have the radiation-dominated era, and the matter. Then you get sort of matter freeze out as things expand fast enough. You end up with protons freezing out and then electrons freezing out. What does freezing out mean? So freezing out essentially is a process that if the energy is large enough in the universe, right, two particles can collide, a proton and an antiproton, produce a photon, a pair of photons, right? But those two processes, if the photons are energetic enough, those two processes are in equilibrium. Because there are enough energetic photons that you can smash two of those together and recreate the two pairs of particles. But eventually, as the energy goes down, the photon energy becomes no longer sufficient given the mass of the particle. So it depends on the mass of the particle, right? The more heavy the particle, the earlier it's going to freeze out because the photons won't have enough energy earlier on. So you can see the protons freeze out, right? And then the electrons freeze out. Interestingly, this is the epoch at which we end up with more matter versus antimatter. Okay, why do we do that? Well, it's this weird thing which is observed even in accelerators today, but we don't fundamentally understand it. It's a symmetry violation. In principle, two photons should always collide and produce two proton, antiproton, or whatever, and vice versa. But it just happens that every 1 part in a billion or so, that doesn't happen. And only a proton is produced and not an antiproton. Okay? And because of that, our universe is made of matter, right? And not antimatter. So this is when that happens. It's called CP violation. And so then we go on, and the universe continues to cool down. This is, of course, temperature versus time here. And eventually you get to the CMB, and only very late, you get galaxies and stuff like that. So this is what the early universe people think. But let's talk a little bit more about this inflation, because that's going to kind of be the start of the whole shebang, right? Okay, so what happens during inflation? So we have this very rapid expansion during inflation. So between this time of about 10 to the minus 35, 36 seconds and about 10 to the minus 32 seconds, the universe expands by at least 20 orders of magnitude. I won't go into why people think it's that much, but it's really large, right? Okay, so let's think about what happens to the small scale, what's going on at very small scales. So you might remember from quantum mechanics that you were always told in school vacuum is empty, is devoid of things. Well, it's not, right? From quantum mechanics, we know from the uncertainty principle that you can get local violations of energy conservation as long as there's sort of a re-annihilation of the things within some very small time, given by that, and that's of course Planck's constant, which is a very small number. So today we don't have to worry because this thing is like 10 to the minus 27 in CGS units, so it's really, really tiny. But when the times are things like 10 to the minus 36, suddenly those kind of effects become important, right? So what happens? So you've got all this pair creation and pair annihilation going on in this vacuum, which been experimentally verified with things like the Hall effect, right? Now let's see what happens at inflation. So happily, all these things are pair creating and pair annihilating, with their in the vacuum, sort of like a fuzz. But then, imagine two particles are created, right, in a pair creation event. So there's a particle and an antiparticle, happily going along, thinking, I'm temporarily separated from my soulmate, and will soon be reunited, right? But then what happens? Inflation. So inflation happens, and all of a sudden the particle ends up way away from the antiparticle, so far away that they are now no longer within each other's cosmological horizon. So literally, that means within the time of the universe, they cannot reconnect. And this is what we mean by these fluctuations are frozen in. So now all of a sudden, this little spot and this little spot, right, have matter, where before they just had energy, right? So it's weird. Literally, it comes from quantum fluctuations, and you know, you would think this is a crazy idea, except that we see this in the CMB. That's the origin of these fluctuations, right? And the spectrum of these fluctuations follows a very specific power law in the power, which we'll discuss in a minute, called the Harrison-Zeldovich spectrum, and that comes directly from this. If you just mathematically work out, you know, how the pair creation and separation would happen, and how much fluctuation should get frozen in at any scale, you get actually that result. We're not going to go through that. It's not a terribly difficult calculation, but in the interest of time, we want to talk more about galaxies. But what I wanted to point out is that it's these fluctuations, of course, that are going to lead eventually to galaxies and planets and, you know, people and penguins, et cetera, right? So what about the CMB, right? The CMB is extremely rich in information about the cosmological parameters for lambda CDM, or any model, really. So what's being plotted here, which maybe you've seen before, this is effectively the temperature fluctuations on any particular angular scale. So essentially, you take the full map, and you ask the question, how correlated on two particular scales? If I look at one point in this map, and I look at another point, let's say 1 degree away, what is the strength of that correlation, right? Like how often do I find, you know, another positive thing there relative to a random thing? Okay, so that's effectively what you're measuring here, and and of course Planck, you know, you can span a wide range of sizes because it has very nice resolution. But you see there's this huge peak here, right? That's the most obvious feature, right? And that peak, and you can almost see it on the maps. When you look at the CMB maps, you notice there's kind of a size, like you would pick out a little granularity, typical size in the CMB map. That's that peak, right? That's your first peak. This is called the baryon acoustic oscillation. We'll tell you in the next slide where it comes from. But essentially, one of the key things to realize about this spectrum, so again, you know, this is the Planck data is in red and the best fitting lambda CDM, which is really an excellent fit for a model that basically has only 6 or 7 parameters. But if you vary those parameters, you get different results. So for instance, the position in angular space of this peak measures the total amount of mass energy. So this is illustrated here. So, you know, here's a case where you have matter density is the critical density, and there's no lambda. So that's the blue line. And then the green line is one where you put 0.3 into matter and 0.7 into lambda today. And it looks almost identical. Peak is almost in the same place. However, if you change the total and make 0.3 and 0, suddenly the peak shifts quite a lot, right? So this is how we know the universe is flat, basically, right? It's the location of that first peak. You can also measure other quantities, like for instance, this is the baryon density. Again, this is going to be very important for galaxies, because obviously galaxies are made of baryons. So again, you know, depending on the baryon density, you can get, you know, different heights of that first peak, right? Now, why is that? Okay, let's talk about where these little baryon acoustic oscillations actually come from. So, you're in the early universe. The universe is very hot, and the baryons are all ionized. So there's nothing neutral yet, right? Pretty much. There's dark matter. Those dark matter fluctuations are growing via gravitational instability. What does that mean? That means, you know, if you're in a region that's a little bit dense, you'll attract more, become more dense, et cetera. Okay, so the dark matter, of course, doesn't care about the baryons or the light or anything like that, right? The definition of dark matter is that it doesn't interact with photons or baryons, right? At least, you know, in the standard CDM picture. So the the dark matter can create these potential wells. The baryons, remember, the baryons are a subdominant mass component, so they're trying to follow, gravitationally just trying to follow the dark matter. But the problem is that they're coupled to the radiation. So the baryons interact with the radiation, right? So as the baryons squeeze down into a potential well, the radiation says, I don't like to be squeezed, right? The radiation pressure increases, pushes back outwards. And so you get an oscillation, right? And so that's basically you're oscillating the baryons in these potential wells. So you can think about the first harmonic, the biggest peak in the CMB power spectrum comes from the fact that, on the first infall, right, that first infall, both the mass of the gravity and the mass of the baryons are pulling in, but on the bounce, you get the mass of the dark matter pulling in, but the baryons are sort of moving outwards, right? So effectively, the first harmonic comes from the two things working together, which is why it's a big peak, and then the second one comes from the two things kind of working against each other, which results in a depressed peak. And this continues. All the odd peaks are high, all the even peaks are low, right? So you can see that the difference in amplitude between these two peaks is going to tell you something about the baryon density, or at least the baryon density relative to the dark matter. And what it's measured is around something like 0.16. So in other words, baryons for the baryon density to the total matter density, so baryon plus dark. So that means baryons are about 1/6 of the total matter density, right? So the interesting thing is the scale of this fluctuation. Well, the first infall really corresponds to the largest possible coherent scale at that epoch. Now, if the universe is 380,000 years old, that means it's 380,000 light years across, right? That's the largest scale at which you can pull things in and have it be causally connected by then, right? So that scale, 380,000 light years at redshift 1100, turns out, as the universe expands, is about 150 megaparsecs today, right? And so you see an imprint of this process going on at very early times in the matter distribution today, and we'll see it in the galaxy distribution a little bit later. Okay, so that's where this all comes from. The key thing is this baryon acoustic oscillation tells you the omega baryon to omega matter ratio. That number is 0.16. Remember that number, it's going to be very important, okay? Okay, so you go down to low redshift now, right? And you ask the question, well, what do we see in terms of these fluctuations? So the way this is usually depicted is with a linear power spectrum, not an angular one, because now basically you have sort of more three-dimensional information. On the CMB, you only have really two-dimensional information, right? So you can do an angular thing. Okay, so this is called the matter power spectrum, and you can measure it. You can measure the fluctuations, depending on your particular tracer. And we won't go into this too much, but on very large scales, you see this cosmic microwave background. Generally, the power spectrum here goes as k to the n, where n, of course, varies along here. So this n equals 1 is the Harrison-Zeldovich spectrum, which comes out of inflation, okay? As you go to smaller scales, however, we're going to effectively higher L's, right? And if you remember in your CMB's power spectrum, the power was sort of dropping as you go to L overall. That comes from a thing called silk damping. Silk damping is just the fact that photons in the early universe can diffuse, right, and wipe out fluctuations, right? So the smaller the scale you go, the more your fluctuations are wiped out. Now, you can see, if you have really good eyes, you can see that effectively, well, you can't really see it in this plot, but effectively, you can see the baryon acoustic oscillations in the CMB. Okay, those are those little tiny fluctuations now taken from the angular scale, where it's really prominent, into the linear scale, right? At redshift, roughly 0. It's not shown here, but these days with the latest galaxy survey, you can actually trace this exactly as well. Okay, you can trace out these baryon acoustic oscillations. Very difficult, because as you see, by redshift 0, a lot of other things have happened in the universe, and the amplitude of those fluctuations or those oscillations has really dropped. On the other hand, you can get many other points along this curve, from things like galaxy clusters, measuring their abundance. That's just large-scale structuring. This weak lensing, which is getting to be very important now with the launch of Euclid, and then the Lyman alpha forest, which we might get a chance to talk about at the very end. Okay. The nice thing about all these is that they all overlap. So they all lie on the single curve. They didn't have to. They're completely different measurements, right? So that's kind of nice, and that's why we call it the concordance model. Okay, so then to sort of, kind of sum up the mass energy budget, right? Again, by using all these measurements, both from the CMB, we can plot these sort of what they like to call banana plots or something like that. So this is dark energy versus matter, dark energy density versus matter density today. And again, you can measure it from a variety of things. You can measure it from the CMB at redshift 1100. You can measure it from these type 1a supernovae, which hopefully you know about. Won the Nobel Prize a few years ago. Galaxy clusters. There's a bunch of other ones that are not even listed here. The point is they all meet at a point. Again, concordance, right? They didn't have to. And so the best, kind of roughly the best fitting model is something like 70% dark energy, 25% dark matter, and 5% baryons, right? So this is about 5 to 1. Note that these numbers are redshift 0, right? Because these are densities, and the densities evolve differently. So the best fitting model for dark energies these days is a cosmological constant. Why do we call it a constant? It's because the energy density is constant with time. So that's this one here. This is a plot of energy density versus expansion factor, which kind of scales with time roughly. You see the matter, well, matter is easy because every time you expand something by a factor of 2, your density goes down by a factor of 8. Okay, so that's just that just goes as a cubed, right? The radiation, however, has another factor, which is redshifting. So not only you reduce the number of photons, but because of your temperature of each photon is going down, so your energy drops by another factor, so it's a to the 4th, right? And that's why it's steeper. Very early on, you had the radiation-dominated era. Then you have matter domination, and now you have dark energy dominating right at the latest, so right close to today, which is one of the main problems in cosmology. It's like, why does dark energy just exactly decide to do it today? That seems like awfully coincidental. So this is called the coincidence problem, and lots of this is why theorists really hate this dark energy model, right? It requires that the dark energy be exactly this value, which is like 30 orders of whatever, some incredible number of orders of magnitude off, in order to be exactly that today. It seems weird, right? Won't talk about that too much. That would be for cosmology. So it all seems very good, but I just, in sort of the last point on cosmology, I just wanted to mention that maybe everything is not quite as happy as it seems, right, in cosmology, because we're getting such good observations now, right? We're getting really, really good observations of both the CMB and the galaxy distribution, so on and so forth. So there's I would say that the biggest two issues right now in cosmology today are, they call them tensions, right? So it's very, nice word. So you basically says this is the Hubble 8 and the S8 tension. So what is the Hubble tension? Well, we haven't talked about this too much, but the Hubble constant is, of course, the rate at which the universe is expanding. It changes over time, of course. It was, higher at high redshift. The universe was expanding faster. But then, of course, with dark energy, the universe is now expanding, accelerating its expansion in that last cosmic period, which is since about 7 billion years ago. So it's about half of cosmic time, right? Okay, so the point is, we now have sort of several different ways to measure quantities. So one of these quantities is this Hubble constant, the expansion rate. Technically, it's A dot over A. So it's not quite the expansion rate, but A dot, it's the expansion rate scaled to the current size of the universe. So when we measure this from the CMB, essentially by trying to fit all this CMB spectrum and so on and so forth, put it into some big Monte Carlo Markov chain thing, we come up with a number something like 68. So this is a history of the measurements of the Hubble constant with time, right? And early on, everything was a little bit higher, but due to some improvements and stuff and higher resolution, Planck was able to measure this better, and it ended up down here, so right around 68 kilometers per second per megaparsec, which means every megaparsec out you go, things are moving away, on average, 68 kilometers per second faster. Okay, that's great. But then you can actually go out and say, well, instead of doing all these crazy things, why don't we just go measure how fast things are moving away from us, right? You can just go look and see what it looks like. Well, that you can do as well, right? And that's these blue points. In particular, what do you have to do? You know, the main issue you have to do is you can measure the recession velocities very easily. That's just from the redshift. So you get an accurate spectrum, you can see the recession velocity. The hard part is getting the distance, because you don't know, like you see a point of light on an image, how far away is it? You have no idea, right? So they use this thing called the distance ladder. One of the most direct measurements comes from Henrietta Leavitt back in the 1910s, right, which is Cepheid variables. So Cepheid variables are a type of pulsating stars who has a fairly well-defined relation between the period and the luminosity. Now, it's hard to measure, well, you can't measure a direct luminosity. All you can measure is apparent luminosity, right, apparent magnitude. But if you can measure a period, right, because you can see how that apparent magnitude is varying, then you get a period. That converts to a luminosity. If you have a luminosity and an apparent luminosity, or a magnitude and an apparent magnitude, then you can get the distance. So this is the idea, right? So you do that, and you use these Cepheid variables, which have now been seen out to reasonably distant galaxies, thanks to even JWST and the latest things. And this is the tension, right? That's many, many sigma. That's about 5+ sigma. Okay, so that's one tension. The other tension has gotten a little bit less notoriety, but it's almost as important, which is this S8 tension. S8 is essentially a measurement, won't go into details of exactly what it is, but it's an amplitude of that matter power spectrum. Okay, so you're measuring some kind of amplitude, and you're saying, do the data points from the CMB line up in amplitude with the data points from all the more local measurements, like, you know, in this case, it's the dark energy survey they're trying to compare to, right? So this is sort of one of the latest cosmology surveys. And this is what they get. So this is the CMB data. It measures a high amplitude, and the galaxy data measures a lower amplitude, right? And again, that's about more than 4 sigma discrepant. Now, what's, you know, one thing is could be just some systematics. We don't know, right? These things are all sort of, you know, maybe the period luminosity relation is not quite the same at higher or out, so who knows, right? But the more exciting possibility, right, is the fact that we're measuring things at 2 different times, right? We're measuring the things at the CMB time, redshift 1100, and the problem is to compare it to redshift 0, we have to assume a model. We have to assume lambda CDM to make, you know, to put it all on the same plot. What if lambda CDM is wrong, right? So that's the exciting possibility, right? So people have been trying to invent things that will maybe reconcile models that will be able to reconcile this. Hasn't been as easy as it sounds. And as we talk more about galaxies, we're going to see that there's some issues, the systematics that arise because of the way the galaxies work, which may be screwing all this up. Okay. So anyway, that was kind of all I was going to say on cosmology, on sort of linear cosmology. Are there any questions about this stuff so far? One question. There we go. Good. Oh, sorry.
You said that one possibility is that we are measuring the amplitude in different times.
Yeah.
Could you explain this better, because I
right.
don't understand?
So essentially, if I go back to this plot, right? These black points come from the cosmic microwave background.
Yeah.
Those things are measured when the universe was 380,000 years old. All these other points are measured, you know, much more recently, like in the last couple billion years. So the problem is you can't really automatically put this on the same plot, right? You have to say that, okay, what happens to these black points in the, whatever, 14 billion years in order to put them all on the same plot. And in order to know that evolution, you have to assume a model, right? And of course, the model we assume is lambda CDM, but, right, apparently doesn't quite give the right answer. So that's what I said. You're measuring things at sort of 2 different times. Any other questions? Oh, yeah, Jose.
So, Romeel, because we are in the exoplanet stuff from, you know,
Yeah.
how to put exoplanet in your budget? I mean, your energy mass budget. I mean, some some of this baryonic stuff could be from exoplanets. Could you comment that?
Yeah, it's so small nobody cares. Okay, so that's the short answer. Yeah, that's the bottom line. Okay, any other questions? Okay, good. So let's get on with actually trying to form galaxies. Okay, so what's the first thing we have to do? The first thing we have to do is the things have to go nonlinear, right? So we know our galaxies are highly nonlinear objects. So I don't know if this movie will work, but anyway, this is just describing gravitational instability, but it's probably something you're mostly familiar with. And the point is that these perturbations grow in the linear regime, grow very quickly. Well, not that quickly, actually, just as the expansion factor. But once it goes nonlinear, the growth essentially goes exponential, right? So I don't know how I can start this exactly. Let's see if I can, there we go. Okay, so you see that very quickly it goes from a smooth distribution, this is just the matter density in a dark matter only simulation, so we're not even including any baryons or anything. And you see these kind of nice filamentary structures and things forming, right? It's kind of cool. This is what we call large-scale structure, okay? Let's see. And the large-scale structure consists sort of, you kind of break it up into a series of sort of sheets, filaments, and nodes. Okay, so what's going on here? So you have some density perturbation, right, that comes from CMB, comes linearly, it evolves forward, grows, 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 eventually goes nonlinear. Well, in general, that perturbation is not going to be spheroidal, it's going to be some ellipsoid, right, with three different axes in principle. Right? Doesn't have to be there's nothing that says perturbations have to be perfect spheres, right? So what's going to happen to an ellipsoidal overdensity? Well, this was worked out by probably, quite possibly, the greatest cosmologist of all time, Jakub Zelzewicz. And what he noticed, proved through a lot of math, is that, interestingly, what happens is that the speed of collapse in each direction is the same, roughly, turns out. It's not totally intuitive why this is, but effectively what that means is that the first axis that's going to collapse is the smallest axis, right? And when that axis collapses, you end up with a sheet, right? And then the second axis collapses, and you end up with a cigar or filament, right? And then finally the long axis collapses, and you end up with a halo, right? And not necessarily spherical halo, it's triaxial. So what you're seeing in this large-scale structure over here is locations in the universe that are in different stages of this process. Obviously, if you have a lot of matter and a lot of gravity, it's going to go through this very quickly in a local region. But if you don't have a lot of matter, right, you might, by 14 billion years, 13.8 billion years, you might still only be in a sheet, or you might, have only gotten to a filament, so on and so forth, right? So it's just essentially, and you saw that in the movie, where things sort of, proceeded much more quickly in the dense regions than the non-dense regions. The interesting thing is, because of this, right, the matter is draining into the higher density regions, which means there's some low density regions, and those are called voids, okay? And so we get voids as well. Okay, so this is kind of the setup of large-scale structure, and that's going to set up, the sort of framework within which galaxies form. But let's sort of we'll come back to that, but let's talk a little bit about that end state of that collapse, which is the halo, right? Because these are going to be the sites where galaxies are going to form, or these dark matter halos. Okay, so. So of course things collapse down and down and down, due to gravity, it just grows. So you can ask the question, what stops this? Why doesn't everything just collapse straight down into a black hole and we're done with the universe and we don't exist? So we don't have to, worry about this. Well, it doesn't quite work that way. And the reason it doesn't work that way is effectively because of tidal torques. So you imagine you have some inhomogeneous distribution of mass. A little region is over here trying to collapse, but it's pulled, it's torqued by the fact that it just happens to be that there's a little more mass, in one direction versus another. So instead of going straight down to the density perturbation, it kind of veers off a little bit, right? And everything is kind of veering off a little bit from where it intended to go, right? Where it would go otherwise. And because of that, right, and it gains speed, of course, as it goes in, and so you end up with very high velocities, and eventually you end up with a whole bunch of things that are sort of bound within a halo that are all whizzing around, all the dark matter particles. Now, as long as it's dark matter, as far as we know, it's not interacting with anything, including itself, so it'll just sort of whiz around forever. And that whizzing is basically mostly due to a dispersion. So it obeys this thing called the virial equation. Okay, so it's very simple to derive in a super easy case, which is that the virial theorem says the kinetic energy is minus half of the potential energy. And this is the final state of a, Alessandro can tell you how to derive it in much more detail. We won't go into that, but at least in a very simple case of a single particle, you're just equating the centrifugal support to the gravity, and just rewriting these, and you get that. Okay, so we say virialized halo. Okay, that means the objects are all sort of the dark matter is all sort of whizzing around each other, and it's supported by its own dispersion. Globally, this can be described by two quantities: the mass and the angular momentum, because of course all that spinning up due to the inhomogeneous surroundings has given the halo a slight bit of twist, right? And so not only is it dispersion supported, but there's a tiny bit of rotation support, but it's not much, okay? And you can calculate this from simulations or even analytic theory, tidal torque theory. And this is a plot of this quantity lambda. Lambda, okay, is effectively a parameter that describes the halos, that is this centrifugal force divided by gravity. Okay, so it's the fraction of the force that is coming from rotation as opposed to just pulling it. So if you just had rotation, how much would you support against collapse, right? And the answer is it's pretty small. So if you look at the numbers here, it's a few percent. So it varies, of course. You can have things that are rotating fairly fast, but even fairly fast means only 10% of the support comes from rotation. That means 1 minus that, like 90% of the support, has to come from the dispersion, right? So mostly stuff's whizzing around each other, but this rotation turns out to be very important for galaxies, right? Because that's how we're going to end up with disks. Okay, so I just want to show you this little movie here. Oh, why is this one not working? Okay, I don't know why it's not working. Anyway, that was a cool movie because it showed it like not in co-moving coordinates, kind of expanding. Oh, there we go. Okay. Oh, is that what's going on? Oh, Jesus. Okay. Well, this might take a while, so let's. But what you would see, I'll just describe it, right? You would see that everything starts off expanding, of course. But then, because there's a dense concentration of matter here, a lot of the stuff goes out, but then starts to come back in, right? And eventually, it's all whizzing around, and you'll see a big dispersion-dominated thing. Well, let's not wait for it. But anyway, that's the basic idea, right? So this is what a dark matter halo looks like. But those are sort of the global quantities, right? We can also think about the internal structural quantities of dark matter halos as well. And again, we won't go into too much detail about this, but just for the sake of forming galaxies, the important thing is that halos tend to follow a roughly universal density profile, which is weird, right? Because halos form in all different regions and so on and so forth, but they can generally be well described by a density profile that was first introduced by Navarro, Frank, and White, and it's some normalization divided by something that scales with the radius times something that's 1 plus the radius squared, where this RS thing is known as a scale radius. Okay, So just to give you a pictorial representation, this is the density profile of various profiles that have been sort of thrown around in the literature from various reasons. The NFW profile is this orange one here. Okay, so what it is at small scales, you see when R is very small, this term becomes negligible and it goes as 1 over radius, right? When R is really large, then the 1 becomes negligible, it goes as 1 over R cubed, right? So generally you're going from something that has 1 over R, which is sort of a cuspy thing in the middle, right, to 1 over R cubed in the outskirts. 1 over R squared corresponds to an isothermal sphere, right, in the outskirts, and then sort of flat in the middle. So that's essentially a constant temperature. There's various other profiles. There's a lot of controversy, particularly about the inner radius, inner slope. We won't worry about that too much. Another interesting consequence of this is the rotation curve. And of course, if you remember your history, right, dark matter was invented. Well, not invented really, but one of the key pieces of evidence was that we get these flat rotation curves, right? That comes from this sort of dark matter profile, but it's not perfectly flat, right? So, for instance, if I were to look, it's really hard to see the orange line here, but the orange line kind of goes underneath here, and then it goes sort of out like this, okay? So the point is, eventually, because it goes as 1 over R cubed on the outside, eventually it kind of turns over. So the rotation curve is sort of flat in the regime where we can measure it, but in point of fact, at very large radii out in the halo, it turns over. Yeah. Yes. Okay. So this is this concentration, right? So that's basically a rotation curve, and then the other thing that's often used to parameterize the halo is this concentration. So the concentration is the size of the whole halo, the virial radius of the halo, divided by the scale radius. So it's just another measure of the scale radius. Okay. Here's some essentially simulations of this quantity. There's a fit to it that the at low halo masses, these are really low halo masses here, like 10 to the minus 5 solar mass halos. People are actually doing simulations that have 10 to the minus 5 solar mass halos. Crazy. I don't know why, it's pointless. But anyway, but if you look at some of these, more reasonably, galaxy-sized halos, you see that there is a trend, right? What sets that trend? Again, very roughly, what sets that trend is the following. As you can kind of envision, galaxies or halos grow hierarchically, which means things start off in very small units, and then they merge together through gravitational instability to get bigger and bigger, right? So small halos tend to have formed at early times. If we see a small halo today, right, it means something that formed early on and then somehow managed to get lucky enough not to merge into anything else. Now, why does that lead to a higher concentration? Well, because the universe is denser at that time. So effectively, the concentration is reflecting the density of the universe at the time that the halo forms. Okay, and so that basically leads to it's fairly mild dependence on mass, but nonetheless, that's really where it comes from. Okay, so that's kind of the structure of halos. Right? And again, we're going to come back to this. What about the number of halos? So now we want to think about, okay, we understand each halo and how it forms through this cosmic web and collapse and a slight bit of rotation, torques, et cetera, et cetera. How many halos are around? Can we actually compute this? And again, the answer is yes. And again, I don't want to go into the derivation of this, but essentially, I'll just explain how the derivation works. So the idea is the following. Suppose you take some patch of the universe, of some radius, right? And that patch of the universe is expanding at first, but it can do one of two things. It can either have enough mass in that patch to turn around, like in that movie that didn't play, right? Or it cannot, right? It'll continue to expand forever. So there's various options. There's sort of, this is just a binding energy criterion, right? This is a total energy 0. This is energy greater than 0. These don't collapse. This one, however, if it has enough mass, it's going to recollapse, right? So you take that recollapse and you ask the question, what is the fraction of mass that's going to end up doing this versus this, right? That's the question you can ask. This is how, and then with the assumption that the fluctuations are Gaussian, you can actually derive a mass function of halos. So the number density of halos per mass bin, okay? Now this turns out to be a really sort of crucial thing. It's kind of pictorially represented here. So it contains several parameters. One is this overall amplitude. M is the mass, of course. And then N, there's this N. What is this N? It's the same N we've already talked about. It's the N of the power spectrum at that particular mass. Now remember, the N varies. I showed you the power spectrum kind of does that, so it varies. Nonetheless, locally you say that, well, I'm going to form a galaxy mass halo, right? My N is going to have, some characteristic value, right? That's that N. So what it looks like, pictorially is something like this, right? So you get a faint mass slope, faint N slope, that's something like minus 1.8. Why is it minus 1.8? Well, remember, at small masses, right, this thing basically, it doesn't matter, it goes as a power law, right? So in the small mass regime, N is something like minus 2, it turns out, okay? So if you plug minus 2 into this exponent, you get 1/6. That part's 1/6, you divide by m squared, right? And you get something like m to the minus 1.8, roughly, right? That's that faint N slope. Then, as you go to very massive halos, of course, the exponential, this is growing, but an exponential always beats a power law, right? So eventually, you're going to get an exponential turnover. And that occurs at some characteristic mass, m star. So you have this faint N slope around minus 1.8, and then you have this turnover at this characteristic mass. And so you end up looking a lot like, if anyone's familiar with a Schechter function, it kind of at least has a similar form, okay? And of course, it evolves with redshift. Early on, at redshift 10, the halos grow and grow. Interestingly, the faint N does not grow very much, right? Because effectively, those small units were formed, but they're merging into larger and larger things. So you can form more small ones, but they kind of are in balance effectively, with losing them to merging, right? So instead, what grows is the massive end, right? And by the way, this is why the abundance of galaxy clusters is a very sensitive test of cosmology. Galaxy clusters tend to have mass around 10 to the 15 solar masses. And this is on the very much the exponential tail, which means you have a lot of sensitivity. These curves depend on the power spectrum exactly, et cetera, through N. And therefore, that's where you get the sensitivity to your cosmological parameters from galaxy clusters. Okay, so this is going to be pretty important. Again, this faint N slope of minus 0.8, as well as the exponential cutoff. Okay, another concept. Oh, sorry. Yeah.
Hi, so in the previous plot, why does the halo mass unit depend on little h? Like, is there a Hubble constant hidden somewhere? Like, why does it matter?
Yeah. Let's see. What's the equation that basically does that? Effectively, it comes from. I'll have to come back to you. I know this, but I can't remember it right at the time. But yes, essentially, because it comes originally from the Friedmann equation, but I'm trying to figure out exactly how that propagates through, to get you the mass dependence, which I can't remember right at the moment. But it's true that basically, your scales, of course, depend a little bit on 1 over h, because effectively that goes as your expansion factor. But these goes as 1 over h as well. I think. Anyway, I'm not going to try to remember it now. Okay, but it's a good question. Yeah.
I have another question. sorry, maybe you said it, but I didn't understand. So I was expecting that at high redshift, I create more massive halos. But here it is the opposite, no? Because this MH is bigger.
Well, these are the halos at that time, the mass of the halos at that time. So of course, you're creating the halos that will become massive halos at early times.
Okay.
But they're not massive yet at redshift 10, right? So this is the halo mass function at that, measured at that redshift. Any other questions? Okay, good. So there's another important concept that now starts to connect a little bit to baryons, okay? Let's ask what the gas is going to do in these halos. Now, in the very simple idea, right, dark matter is the dominant mass thing, right? So dark matter, it kind of bullies the baryons into doing whatever it wants, right? So when the dark matter collapses into a halo, the baryons are kind of just dragged along for the ride. So that means that the resulting halo should have this same fraction of baryon to matter ratio, in this simple picture, as the overall cosmic ratio, right? However, once you get inside a halo, right, things can start to happen. And particularly, of course, we talked about how how the dark matter is collisionless. So it can wander through each other, no problem, right, and just stay in this nice, stable, dispersion-dominated configuration. Not true of the baryons. Of course, you throw two things of gas together, it will do all kinds of things. It will shock, heat, and so on and so forth. So once it starts to shock heat, right, it essentially creates, it has a temperature associated with that. The temperature has to be such that it balances the gravitational potential, right? And you can calculate what this temperature is for a halo of a given mass, mvir. And this is this thing called the virial temperature. So this virial temperature essentially ends up being, in the absence of anything else, the gas is going to fall into this halo, start smashing into each other, and in order to support itself against collapse, right, it's going to have to get a particular temperature that effectively holds it up by its pressure. And that temperature is this virial temperature. Depends on some things. These are like, this mu is the mean molecular weight, which depends on the hydrogen abundance, the helium abundance, and the metal abundance, so on and so forth. We won't worry about it too much. Overall hydrogen abundance, as you know, is about 75% of the mass. So the gas then settles into this sort of thing where at each radius, it's hydrostatic equilibrium. Hopefully some of you are familiar with this quantity, or this concept, right? Where the pressure gradient has to be just enough, to offset the gravity at that radius, the gravitational force. And that creates a balance between the self-gravity and the internal pressure, where you have this sort of hot gas-filled halo with this virial temperature. Okay, so that's just sort of what the gas is doing. We'll talk a little bit, of course, so what happens next? Okay, so the other thing about baryons that's very special, right, is that baryons can cool, right? Baryons can radiate away their energy because they have atomic levels, et cetera, right? So now, radiative cooling is a process that goes as the density squared. Why? Because it requires two things to hit each other. You excite an atom, the atom then falls back to its ground state or a lower state, emits a photon, that photon escapes to wherever, and you've lost some energy out of the system, right? So this is the process known as radiative cooling. Cooling has a variety of different physical processes. Maybe you've studied some of these, hopefully, in some radiative processes type course. You can get collisional excitation, collisional ionization, recombinations, et cetera. And then finally, at the very high temperature end, you get everything is ionized, so you just get free collisions between electrons, right? It's all collisions, but of different sorts. The point is, you get some sort of curve that, if you just have hydrogen and helium, which is all that comes out of the Big Bang, you get a curve that looks kind of like this, right? So there is no cooling, roughly, in primordial plasma below around 10 to the 4 Kelvin. This is a key point. Right? 10 to the 4 Kelvin is a very magic number. Why is it a magic number? Where does this 10 to the 4 come from? It comes from the fact that effectively that's, the hydrogen atoms, 2-to-1 transition or whatever corresponds to a photon that's roughly that temperature, okay? So that means you can't cool. There's no atomic transitions left for you to cool at these lower energies, right? But then it goes quickly up, and then you have helium here. Of course, you don't just have hydrogen, you have helium as well. So this is a helium peak, and then you have this sort of tail for the free, completely unbound, ionized gas. If you have metals, right, so heavy elements, things really start to be dominated very quickly by metals. I'm just sort of informing you of this. We're not going to use this so much, but it's important to realize metals are very, very important for cooling. So one of the reasons why chemical enrichment is so important in galaxy formation is because galaxies form by cooling their baryons, and the metals are really important for this. And you can see that here. This is just a tiny bit of metal. So this is the black curve is, okay, some roughly zero metallicity. I don't know if you know about this. This is effectively the metallicity, the iron to hydrogen ratio scaled to solar value taken the logarithm. All right, so that's what these little brackets mean, okay? It's just kind of another astronomy notation thing. So this is essentially 10 to the minus 10 of the solar metallicity. So effectively 0, right? This is a tiny bit compared to something, the solar metallicity being the metallicity of the sun, right? And this is the solar metallicity right here, right? So you can see that basically once you start to get above about 10 to the minus 2 solar, which is only 1/100th of the metallicity of the sun, right? You start, that's the green curve here. Suddenly, like this curve, which is this black curve right here, right, actually starts to be dominated in most places by the metal cooling. So even 1% of metals can really impact the cooling, right? And when you get to 10%, and certainly when you get to solar, that's that red line, except for this particular, edge here, you've mostly forgotten about the primordial cooling, right? So this is why we have to care about metals and supernovae that create them and everything, right? I told you galaxy formation is complicated. Okay, so what happens? So the baryons are able to cool down, right? They're able to get rid of their potential energy, unlike the dark matter, right? But remember, we have this lambda, right? We have this lambda that's the rotation of the halo. Now, when, on large scales, that doesn't provide any sort of much support, few percent, as we said, for the halo. But now imagine that the baryon can get rid of all its sort of potential energy, right? And sink down. Well, what's going to stop it from collapsing all the way? Well, the only thing that can stop it is the rotation, is this sort of centrifugal force, right? And so it can collapse down in the vertical direction, but it's like we all know about merry-go-rounds, right? You can't collapse in the direction of in the plane of rotation. So essentially, you end up with something that results in a galaxy disk, right? And this is a very common thing that happens in all kinds of astrophysical systems, right? So you form this galaxy disk. And then once the disk is formed, of course, that's when all the fun starts to happen, right? You can start to form stars, you can start to form, supernovae, you can do all kinds of craziness. Okay, so again, this is all sort of just setting up how galaxy formation is going to work, right? Once we're just setting out the ingredients right now. But one thing I did want to talk about is this idea of essentially hot versus cold halos. Okay. What does that mean? What am I talking about versus hot? I just told you that halos always heat up due to the shocks and everything, right? Well, not necessarily, right? Because if you imagine, there's a virial radius, right? Gas is going to shock heat at the virial radius, right, and going to heat up. At some point, the density is large enough such that the cooling can exceed the rate at which it can be shock heated. And then the galaxy can cool down. And this is known as the cooling radius. So turns out in a massive halo, right, the cooling radius is tiny. Why? Because again, massive halos tend to be fairly diffuse, right? They're big diffuse things. And so this cooling radius is quite small, and so the gas is going to fall in, it's going to shock heat, it's going to form this big virialized, virial temperature halo, and only in the very center can it actually cool. But what happens in small halos? Now, we talked about this concentration. If you remember, the concentration is higher in small mass halos. Concentration being higher means the densities are higher, which means the cooling is more effective, right? Because it's an n-squared process. You can actually get a situation where the cooling radius exceeds the virial radius. Nothing that prevents that from happening. There's nothing to say the cooling radius has to be inside. It could be that the density even out here is sufficient that it can cool away its energy that it would otherwise shock heat. Right? Does everyone get that concept? So the gas is coming in here, it starts cooling, cooling, cooling. It says, oh, I should be shock heating here, but my cooling rate is so fast that I can't do that. I stay cold. So what happens if I stay cold? Well, if I stay cold, I have no pressure support, which means I just kind of fall straight to the center. Now, this is an illustration of a simulation that shows this, right? This is effectively, well, let's look at this plot right here. This is the inflowing flux per solid angle, right? And so this is a forming halo right here. Here's the gas coming in, and you see it comes in along these streams. These are these filaments, these cosmic web filaments that we talked about. They enhance the density, right? Because they're actually channeling the density down these cosmic web filaments. And they allow the gas to get to the galaxy very, very quickly. So when you have these cold mode halos, right, maybe the gas shock heats out here, but basically much of the gas is able to just run down these filaments, cool very, very quickly so that it never shock heats, right? Now, what's interesting about this? It turns out that when you run calculations and do it with all the metal cooling and everything, because you need to do it very properly, turns out the transition between this fast cooling and slow cooling halos, these hot, so this is a cold mode halo, right? Because everything is coming in cold here, never shock heats, and this is a hot mode halo because things shock heat first and then cool down, right? That transition is right around 10 to the 12 in halo mass. Now that is a very special number, as we will see, right? It happens to be the halo mass of the Milky Way, but it's also, we're going to see, a lot of different things happen at that mass scale. And a lot of it happens because of the difference between the way that things work in cold mode halos versus the way things work in hot mode halos. Okay, the last thing I just wanted to show, because it's fun, right? And again, it's going to be important. It's like, okay, we know that galaxies have disks, and they are in disks and are in ellipticals. How does that happen? Well, as you probably are aware, you can smash two disks together, and you can get an elliptical, right? So this is just a little simulation of two disks being smashed together, all kinds of nice views and things like that. You see, some kind of big tidal features, et cetera, right? And eventually, right, this thing will settle down into kind of a disordered configuration, right? Yeah, it's going through all these cool stuff here. But this is all basically stuff that you can see in the real universe. Galaxies like the antennae look like this, right? So it's pretty cool. You can settle down, and eventually you kind of settle down into a big elliptical-looking thing. Okay, fine. So generally, this happens when you have a major merger, something like greater than 1 to 3 in mass ratio between the two things, maybe 1 to 4, depending. You can get minor mergers as well. The other thing that you can do, right, is that you can actually, a merger between disks doesn't always to an elliptical. Why? Because if the merger has already a lot of gas, it still creates a sort of, first you have a gas disk. You don't even see a disk. This is too early on. But eventually it'll settle into a little bit of a disk. This is a hydrodynamic simulation of a formation of a Milky Way-like galaxy, right? And now you start to see, something is coming into a disk-like form. But here it's going to merge with something. And all it does, it still has a disk, because there was so much gas around that it quickly settled down into a disk. On the other hand, we've now produced a bulge down in the center of the galaxy, right? So these mergers, if they don't lead to full ellipticals, they can already lead to formation of the bulge, right? And so this is kind of how we get, something like the Milky Way with a disk and a bulge, so on and so forth, right? Okay. Actually, I'll skip that leave that for the next time since we're out of time. But essentially, this is a summary. Yeah. So we have our cosmological model that sets the large-scale structure. That sets the sort of the framework within galaxies form. Then you get these gravitational instability that forms the cosmic web. You get the halos. You can actually predict the number density of halos, has a very particular functional form that we'll see again. And then you are able to radiatively cool, perhaps, or shock heat and then radiatively cool the baryons, forming into a rotationally supported disk, which then merge into ellipticals, right? Voila, from this, you get the whole galaxy population, right? Great, we're done in one lecture. Okay, not quite, as we'll learn next time. Okay, see you later.
Okay, we have plenty of time for questions.
So thanks, Romeel. Could you please go back to the dark matter halos slide where you defined the spin parameter J?
Yeah.
Yeah. So this y-axis P in scale of lambda. What is exactly that? It's like
sorry, I should have.
probability
It's just a
density function.
histogram.
Huh?
It's just a probability density.
Okay, yeah. So that leads into my question. So we are more likely to form then low spin parameter structures and halos than high spin parameters.
Well, yes, exactly. Your typical spin parameter is around 3%, maybe.
Okay, so and that's follow up. So next question. So what is like the minimum spin parameter that you need to have in order to form like a spiral galaxy?
Very, very small, unfortunately. So the reason is this. If you think about the size, let's just take the Milky Way. The size of the Milky Way halo is 200 kiloparsecs, roughly, right? The size of the Milky Way disk, like the scale factor of the Milky Way disk, a few kiloparsecs, like maybe 3 or 4, right? That means the disk is shrinking down by a factor of not quite 100, but let's say, I mean, Milky Way is pretty disky, by a factor of 100, right? That's, if you just conserve angular momentum, right, then even something of 0.01, shoot, wrong button, even something 0.01 forms something as disky as a Milky Way, right? And so that was the first thing people thought. And this is the Egan-Lyngden-Bell-Sandage model. It's like, oh, maybe just ellipticals form from these things over here. Turns out, no, because as you see, essentially anything will form at least an SA galaxy, right? And the things that actually can collapse straight into ellipticals is, at most 1% or something like that, whereas in the real universe, we see half the galaxies are ellipticals. So clearly, the dominant way of forming elliptical cannot be to just, take this end. It's basically just from angular momentum conservation, from shrinking down the size.
Okay, thank you.
I have a curiosity related to this plot exactly. So this you can, in principle, even compute from the power spectrum, right?
Yes,
Right, so
kind of. Yeah.
How does that depend on the on the slope of the power spectrum on the other parameters like this? Is this a factor, or is completely dominated by just tidal torque in a regime that this doesn't really matter? It's just volume.
Yeah, that's a good question. I actually don't quite know the answer to that. So there is a whole branch called, keep doing that, tidal torque theory, that effectively, sorry, computes how much angular momentum is transferred from large-scale structure into halos. And it's true that there is some sensitivity to the power spectrum on that. But I suspect that given the current cosmological constraints, the constraints are such that there isn't that much sensitivity to this. And it's very difficult to measure this directly, right. from anything.
I take advantage of the fact that I have the microphone.
Right.
So you didn't mention central black hole, no?
Not yet. Yeah.
Okay. But can you anticipate, does it play a role in, say, changing the dark matter to baryon ratio and so on? It does it?
Yes.
Okay.
In fact, wait till lecture 3 and we will talk all about
Okay.
that.
More questions, guys? Here.
Actually, my question is related with Ricardo. I mean, you did the simulation for the formation of a galaxy, but without black holes. If you introduce a black hole, would it be different, the simulation?
So dynamically, no, right? Because black holes are tiny on these scales. So your typical black hole, even in a massive elliptical, is about, you know,
Some
at most
kilometers.
1% of the total mass, right? So it doesn't really have much dynamical effect, other than right in the center of the galaxy where it, you know, where it can dominate its surroundings, and that's important. So it turns out to be very important for forming galaxies, but not because of dynamics, more because of, turns out, feedback, as
Okay,
we'll
so
discuss.
just the kind of amount of matter inside of the nucleus would be different.
Yeah, so just to give, I mean, sorry, just to give you sort of a you know, rough estimate. So we said that 5% of the total mass energy of the universe is in baryons. Of that, about 10% is in stars, less than that actually, but let's say 10%, right? So that's now 0.5% in stars. Black holes are actually about, you know, 1/100th of that. Sorry, my throat is acting up here. About 1/100th of that, right? So that's the kind of fractions you're talking about. They're very, very, very small.
Okay, great. Thank you.
More questions? There.
In the large-scale structure,
Yeah.
some regions has lower density of matter.
Yes.
These regions has more dark matter. I mean, the ratio between matter and dark matter.
So
Change?
in the simple model, no, right? So that's a void in the dark matter. And because at those very low densities, the baryons can do nothing but sort of follow along with the dark matter, there'll be the same amount of baryons, you know, roughly 16, 17% of the total matter in that will be baryonic, right? So those are regions where, you know, you can really probe the baryon density if you could somehow measure it, but that's, of course, not so easy.
Excellent lecture. Thank you, Romeel. So in this diagram with metallicity that you showed, you know, this from solar 1 to... Yeah,
Yeah.
exactly, this one. So
Yeah.
you didn't mention the pop 3 stars. I mean, I figured out at some point of that pop 3 comes, right? Again, it's...
Yeah. Again, that'll be lecture
Yeah,
4,
I mean,
so
yeah.
we will cover
I
a
would
little
like to
bit.
put more star physics in this stuff, right? At
Yes.
which point metallics come from star, from supernovae, and finally put some planets at some point of that, you know?
Yes, right. So population 3 stars, I guess you guys learned about population 1 and 2 and 3 stars already. You know, generally come below about metallicity of -3, right? Maybe -4, -5, not quite sure, right? So when you're at those metallicities, you're pretty much dominated by the hydrogen-helium cooling, right? You're not really sensitive to the metallicities produced by, with one exception, which is down here, right? Now you can ask the question, what is this line, right? This line right here, why does it, you know, if there's no primordial cooling, how do you get this little bump? The answer is it's molecular cooling, right? So one thing that primordial gas can do is form into H2, so just stick 2 hydrogens together. The problem with that is that essentially molecular hydrogen is very, very difficult to form. Essentially you need for various reasons, you need a 3-body interaction to form pure molecular hydrogen. You would think you could just smash 2 hydrogen atoms together and get molecular hydrogen. Doesn't work that way, because effectively the potential doesn't allow you to do that, right? So you have to basically go through a bunch of stages with deuterium and stuff, and that turns out to be extremely. So it is possible. It is possible, and the very first population 3 stars had to form that way, because otherwise how else do you know, you can't form stars if your temperature is 10 to the 4 Kelvin. It has to be like 10 Kelvin, right? So you have to do that, but that's why population 3 stars are so rare, is because it's very, very difficult to do. As soon as you start to throw some metals, you can increase that quite a bit, but what really increases that, of course, which is not shown here, is the dust. Because the best way, and the way that molecular hydrogen forms in the Milky Way, is actually being catalyzed on dust grains, weirdly enough. So you have a dust grain, some sort of silicate or carbonaceous compound, and the surface of the dust allows the hydrogen to stick, and the two hydrogens happen to be close to each other, can actually form molecular hydrogen there, right? So, that's how we get molecular hydrogen stars, but in population 3 regime, you can't do that, and that's why it's so difficult. Yeah. And it's a whole other question to understand dust. That's like another set of lectures.
More questions?
Maybe we can go for coffee.
Well, I have another curiosity before we go for coffee, since I have the microphone. So
okay.
the picture that you show of the fast and slow cooling and the streams, yeah, that's right. So how far down in scales can you push this? I mean, you talked about, you showed the picture of concentration down to really small scales and so on. This, I mean, well, this might as well work for, for 10 to the 12 or 10 or 8 or 6, or how far down can we push this?
Good question. So essentially, the virial temperature, okay, so there's a couple of interesting virial temperatures to think about, right? The virial temperature of something like the Milky Way, which is right around 10 to the 12 solar mass halo, is something like a couple million degrees, 2 to 3 million degrees, okay? So that's a good number to keep in your head. That's pretty high, right? It's way above, 10 to the 4 and everything. The difficult part is forming stars or forming galaxies when your halo virial temperature drops below 10 to the 4 Kelvin, right? Because 10 to the 4 is this magic number, right? You can't cool. So if your halo cannot heat the gas up to 10 to the 4, you have no cooling channels, right? So basically, that corresponds to a halo mass, just it actually depends a bit on redshift. So, but in the early universe, it's around 10 to the 8th solar masses, which means there's a cutoff, right, at low masses where you can't form galaxies anymore no matter what you do, because the cooling radius doesn't exist. There's no cooling ways, right, until you get metals, et cetera, et cetera. So that's really where it runs out, is at 10 to the 8th in halo mass. So yeah, when you have this sort of, very optimistic 10 to the minus 5, these aren't forming any galaxies, right? The only things that can form galaxies are going to be, I mean, these are all theoretical calculations, right? So is things above here, and in fact, at low redshift, it's actually a bit higher. It's around 10 to the 9. So there's some evolution with redshift. Yeah.
Okay, last chance for questions. Otherwise,
as final comment, just for Romeel have many students that think about the PhD in the next years, right? So you talk about this COBE mission, blah blah blah. So the Nancy Broman will be probably the next step. So you could figure out in the next class how, I mean, this satellite will add to this baryonic oscillation. You don't need to answer now, but it's
yes,
yeah,
that's right. There's a huge number of unsolved questions in cosmology. I've just highlighted a couple of the ones that are recent that you might hear about. Again, this is mostly about galaxies, so we're not going to talk too much more about the cosmology questions. Nature of dark matter, dark energy, et cetera, are all these super interesting, but we can't cover everything, right? So we're going to, next time, we're going to really start to dive into the galaxies, and believe me, there's plenty of questions there too. So there's no shortage of things to work on for PhD projects. And
okay.
you'll see some of those things.
Great. So let's thank Romeel again. And let's break for coffee.